My name is Joseph Moon and this is the Lab 2 falling motion of a falling object. Sections I will cover include introduction, models, experiment, code, discussion, and conclusions. The purpose of this lab is to measure the motion of a falling object, and the initial condition is an object is at rest before it is dropped. The system is a stress ball while the surroundings is everything else, and the two models that I will compare are graph with gravitational force and a graph with gravitational force and drag force. A preview of the results is that the model that took into account gravity and drag force will be more similar to the experimental position than the model that only accounted for gravity. Some models we will need to know are Newton's second law, gravity force, and drag force. Newton's second law states that the change of momentum of a body is proportional to the impulse impressed on the body. And another form is F net equals ma. Gravitational force is one of the four fundamental forces and is an attractive force between two objects. Fg is equal to mg and is in the y direction. Drag force is a resultant force between molecules in the atmosphere and the falling object. Fd is equal to negative b times magnitude of v squared times v hat. B is the proportionality constant while v is the object speed. For this experiment, the procedure is we want to drop the object used from a height and record a video of this motion, upload the video to Tracker and track the position of the stress ball at certain time frames, and create two computational models on GlowScript, one for the ball's position as a function of time only accounting for gravity, and one for the force of gravity and drag force. And then we want to compare the experimental data with these two graphs. For the observed data, I dropped the stress ball from a certain height and then tracked the position, and delta t is equal to 0.750 seconds. Initial position of the ball is 2.0310 meters, and initial velocity is 000 meters per second. This is the code on GlowScript for the gravity-only computational model. I have my input ball mass, and then I input my initial velocity and initial position from the experimental data. Delta t is equal to 124 because it's a 24 fps video, and then b is equal to 0 because it only counts for gravity. This is my code for the gravity and drag force model. So I only changed the net force and the proportionality constant, which I found this constant by doing trial and error so that the model would more accurately reflect the experimental data. I wanted to make sure that the final position of the experimental data aligned with this model. So I found the proportionality constant to be 0.0791111, and then for the net force I said that it is equal to weight plus force of drag. This is my data for the gravity only model. The left is my position versus time, and the right is my velocity versus time. And this is my data for the gravity and drag force. When I compare the two models along with the experimental data on the same graph, I can see that the gravity and drag force model is closer to the experimental data than the gravity only model is. So some possible errors that may have occurred include inaccurate position tracking, which is when the red dots tracking the motion of the ball may have not been on the same center of mass, and then an accidental applied force may have been applied when I dropped the ball, and then an inaccurate camera angle may have shifted the data. So which model predicts terminal velocity? The model that included the force of gravity and drag predicts terminal velocity because the velocity graph shows nonlinear velocity growth that eventually plateaus, while the velocity graph for only gravity displays a linearly increasing velocity. So if we go back to the graphs, this is the graph of gravity and drag force, and you can see that it is plateauing near the end, while the graph of gravity only has a constant velocity growth, which means an acceleration. And then what if the object was thrown downwards? When I input a force or initial velocity into the code, you can see that there would not be a change in terminal velocity, but only a change in when that terminal velocity is achieved. So it would not change because it is only dependent on the magnitude of drag force being equal to that of the force of gravity. The left graph is the graph when you apply the initial velocity, and then the right graph is when you don't have that initial velocity.